Hello out there in internet land. This is Chris Compton at the Blue Sea Ranch studio. There's been a lot of consternation and stress and pain and suffering on Ohm's Law forever and ever and ever. This is a little tutorial thing to help you guys figure out how to use Ohm's Law, and hopefully it will help you. It should help you. If it's not helping you, then turn it off and do something else like that. Okay, so you can see it's Ohm's Law Primer. Ohm's Law is typically put out in these triangle shapes, and there's some things to know about these triangle shapes right off the bat. The first thing to know about is the line through the middle is the divide by line. So anything that is above the line is divided by things below the line. All right, so amps into watts will give me volts. Volts divided into watts will give me amps. Resistance in ohms divided into volts gives me amps. Amps divided into volts gives me ohms. All right, so, and we're going to go on with that and on with that and on with that until you get it. The thing down here below, the X, the X sign means multiply. So we'll move on, but that's just something I wanted to make sure you understood, that this line is divide by, the X is multiply. So, the beauty of Ohm's Law, if you know any two electrical values, you can find the other two. So, for instance, if I know, as it shows here in the slide, if I know volts and amps, I can find resistance. And just so happens that if I know volts and amps, I can also find wattage or power. But we'll get there. We'll get there. So, Ohm's resistance is not known. That's why the R is X'd out with a red X. All right? Amps and volts are known. The solution is to divide amps, boom, down here it's 10 amps, into volts, 120 volts, and that will give you the resistance in ohms. And you can see here, I did the division, 120 volts divided by 10 amps, and this would be 12 ohms resistance. There you go, just like that. Here's another one. If you don't know amps, but you know volts and ohms resistance, same deal. You've got volts, 120 volts. You've got resistance, 12 ohms. You divide 12 into 120 volts, and it's going to give you 10 amps. The answer is there. All right. Are we doing this okay so far? I hope so. The next one. If you know any two electrical values, you can find the other two. Well, this time we don't know voltage, but we know amperage and we know resistance. So what do we do here? We use the multiplication sign, the X, and it's very simple. We go 10 amps times 12 ohms resistance, and that's going to give me 120 volts. All right. The next one. Are you getting tired yet? I am. But anyhow, here we go. The next one. Now we're changing up here and we're going to find wattage or power. P for power, which is wattage in electricity. We have here, we're going to find power or wattage. P stands for wattage or power. We know it's a 1200 watt load. We know it's a 120 volt load, but we don't know what the amperage is. Right? So maybe this is a 1200 watt electric heater. We know that it's 120 volt because that's what it says on the nameplate. To find out how many amps this thing should draw, we're going to divide 120 volts into 1200 watts, and we're going to get 10 amps. Pretty straightforward, pretty simple. You all have a calculator on your cell phone. That's the best place to go for this. So get your cell phones out or your calculator if you happen to have one of those old-fashioned devices, and do the math. Next one. We don't know voltage, but we know wattage, power, and we know amperage. Just another version of the same thing. We've got 1200 watts, we've got 10 amps. 10 divided into 1200 is 120. So it's 120 volts. Next one. We don't know wattage. We don't know the wattage for this device, but we know the amperage and we know the voltage. Once again, use the multiplication sign here. That's 10 amps times 120 volts. And what's it going to give me? It's going to give me 1200 watts. Just remember what the symbols are, how to manipulate the symbols if you know two values, you can find the other two. So this cartoon says it all. I love this cartoon. I saw this cartoon years ago. It's still out there. You can find it on the web. It's out of an old Carrier slideshow. It takes 1 ohm. This is basic Ohm's law, period. At the simplest pictorial version of it, I like it. It takes 1 volt right here to push 1 amp right there, although it looks like he's kicking him, through 1 ohm of resistance. All right? So if you use Ohm's law to calculate this, it's pretty simple. I've got 1 amp times 1 ohm, 1 times 1 equals 1 volt. Okay? I've got 1 amp times 1 volt, 1 times 1 equals 1 watt. Or you can do the division, you can go 1 into 1 equals 1, and it goes on and on. Where people get screwed up, or where I see students get all panicky and weirded out on this deal, is when you change from 1. Instead of just 1, you could, like the previous example, I'm using 10, 120, 1200, etc. But if you just plug the numbers in the right places, you can calculate this stuff all day long without missing it. So here's another good example of how this works, Ohm's law and electricity flow in general. It's very good to understand the values of electricity. Yes, it is. This comparison is accurate in all aspects. And what we're looking at here is a comparison of electric system versus a water system. And this comparison is a great comparison. It works just the same way. Water and electricity work the same way. We've got water pressure, that equals voltage pressure. We've got nozzle restriction, that equals Ohm's resistance. We've got gallons per minute or gallons per hour flow, that's our amperage. And then total gallons flow is wattage. Okay, you should already understand water dynamics well, so use this comparison to understand electrical dynamics also. It's a great comparison of how things work. If you know water, you've been playing with water all your life, I assume, electricity works exactly the same way. The one thing I would say about wattage is, the one thing you have to remember about wattage is, just like gallons per hour perhaps, or gallons per minute, wattage is based on a unit of time. And our typical time scenario for wattage is hour. So when you pay your electricity bill, you're paying for kilowatt hours. In other words, 1,000 watts per hour, or 10,000 watts per hour, however many kW you're using. Here you go. You understand the relationships between the electrical values is important. It's very important. That's the whole purpose of Ohm's law, by the way, and I haven't mentioned that yet, but I'm going to beat you on it. Ohm's law, I mean, do we use Ohm's law in the field? No. Are you out there on a daily basis calculating, I know my voltage, I know my resistance, so I need to know my amperage? No. You don't go there. Ohm's law and the study of Ohm's law and the exercise of Ohm's law, particularly the exercise of Ohm's law, is to cause you to develop in your head a relationship between the measurements of electricity and how they affect each other. That's what it's all about. You do need to have that relationship understanding. All right, so that's what Ohm's law is primarily for, is to help you develop that relationship. Is it utilized in the field? No, it's not utilized in the field. I hate to break that to you, but that's the way it is. But if you do have that relationship connection between amps, volts, Ohm's resistance, and wattage, then you're good to go with electricity. All right, so if the pressure 120 volts is constant and the restriction to flow, Ohm's resistance, is increased, what happens to the flow? All right, so here's a relationship. Previous flow, 10 ohms at 10 ohms, 120 volts at 10 ohms was 12 amps. The new flow, with Ohm's resistance increased, I doubled the resistance, so now it's 120 volts divided by 20 ohms, and the flow went in half. So by doubling the resistance, in this case, the amperage, the flow goes in half. Resistance doubled causes amperage to drop by half. Note the voltage, the pressure stayed the same, and this is proven by using Ohm's law. Conclusion. If voltage pressure stays constant and resistance, ohms, is increased, the flow reduces. Certainly, if you increase the resistance against a pressure, I don't care if you're talking about electricity, electrons, or if you're talking about water, etc., if you increase the resistance, the flow is going to reduce. Conclusion: if voltage pressure stays constant and resistance ohms is reduced, the flow increases. Sure, open that nozzle up wider. Now I get more gallons per minute or gallons per hour. In the case of electricity, now I get more amperage. Conclusion: flow, amperage, is a result of voltage, pressure, and resistance ohms. And that's really the crux of the matter. Amperage is the actual electrons flowing through the conductor. And remember, electrons are a real piece of something that have mass and take up space. All right, so we're flowing these real pieces of something just like a gallon of water, flowing them through the conductor, and that's what electron flow is all about. Truths related to the relationships between electrical values. HVACR technicians do not design or supply the voltage. No, that's not our job. That's the job of the utility. We just deal with what we got or what they're providing. We deal with what's provided into the system. 110 to 125 volt single phase. It's L1, neutral and ground, or 208 to 240 volt single phase. That's L1, L2, and ground. Or in the three-phase market, 208 to 440 volt three-phase, L1, L2, L3, and ground. And when we find that the provided or the supplied voltage is not correct, that's when we start troubleshooting to find out why. Did we lose a fuse somewhere? There's been more than a few times where I have found the utility is not providing the right voltage to the building for some reason. They had a transformer failure or something out on the distribution side. HVACR technicians do not design the resistance of a load device. No, we don't. There's plenty of engineers out there that are designing the motors and designing the heaters, the resistive loads, etc. All the loads that we deal with in HVACR are somebody else's creation, somebody else's design. So we don't really have anything to do with that situation. We are using what we have to work with. We deal with what's provided in the system. We verify that the load device is functional and operationally safe. Yes, please. And we troubleshoot when we find the load device will not operate with the correct voltage applied. That's what we do. But we don't design the resistance of a load device, and we don't design or supply the voltage. Those are things that we get to work with. And in addition, HVACR technicians do not design or specify the amperage of a circuit. No, that's not our job. Our job is to check the circuit, make sure everything is as it should be, and sign off on it or try to figure out why it's not as it should be. Often amperages is the first check of troubleshooting, and boy is it. Amperage is such a quick, easy check. You guys all have your clamp-on amp meter. You all know how to read a data plate, I hope, where it says what the amperage should be. You should always read the data plate amperage before energizing a circuit. Heck yeah. If you don't know what to expect to see, how do you know you'll be seeing something right or wrong? You don't. So check that data plate, find out what the amperage is supposed to be before you turn the thing on. Maybe it's supposed to be 10 amps and you don't know it. And you turn the equipment on and it's pulling 20 amps. If you don't know it's supposed to be 10, you're going to sit there and watch something burn up, which is not a good thing. Not a good thing. So check the data plate before you energize the circuit. And after verifying the correct voltage and load device functionality, we confirm proper amperage draw. If we don't have proper amperage draw, then time to troubleshoot, figure out why. Now here's a last little ditty that I see a lot of technicians worrying about, maybe not technicians, maybe students in school that are worrying about this. Find the total resistance of a parallel circuit. Well, once again, let me tell you, if you ever do this in the field, i.e. walk up to a parallel circuit, which is most of the circuits that we work on, by the way, they're usually large parallels, and somebody says, well, what's the total resistance of that circuit? You're going to look at them cross-eyed and you're going to go, who cares? I don't care. Parallel circuit total resistance, why would I care? I can't think of hardly any situation where I would care about the total resistance of a parallel circuit. Now there may be some of those situations in electronics, direct digital, those kind of things, but the average service call, technician troubleshooting thing, total resistance of a parallel circuit is just totally not worth knowing. Why would you know it? You wouldn't care. But the problem is this is a common exercise in the education of Ohm's law. So let's go through this the hard way first, and then let's talk about the easy way. All right, so if you're going to get the total resistance of a parallel circuit using the resistances of the various loads, and I've got 4 loads here, 120 volt power supply, I've got 4 loads, 40 ohms, 30 ohms, 20 ohms, 10 ohms, made it easy just for the brain tease. So the way the spiel goes is total resistance of a parallel circuit would be found by finding the reciprocal of the sum of the reciprocals of the individual resistances. And as I say right here in red, big pain, all right? So what it means is the math that I've done here. I've got R1 at 1 over 40, and 1 over 40 would be the reciprocal of 40. Remember, up here, to get a reciprocal, you divide a number into 1. And we got a 40 ohm resistance here. We're going to divide it into 1, and that gives me a reciprocal of 0.025. So, and if you want to use your phone calculator, here's the way you go for it. I've got 1 divided by 40 equals 0.025. So that would be the reciprocal of 40. If I want to find the reciprocal of 0.025, I'd go 1 divided by 0.025, and guess what? It's 40. So you can reciprocal back and forth and find your way around. So that's what this is about, is here I have the reciprocal of the first resistance, R1. Here's the reciprocal of the second resistance, R2, reciprocal of R3, and the reciprocal of R4. Here's the numbers that those represent: 0.025 for 40, 0.033 for 30, 0.05 for 20, and 0.1 for 10 ohms resistance. So I add those up, and they add up to 0.208, sum of reciprocals of the individual loads. And then, the big trick here is then I need to find the reciprocal of 0.208. We're going to go back and we're going to find the reciprocal of 0.028, so it would be 1 divided by 0.208 equals, there you go, 4.80769,231. Well, good enough is 4.8. 4.8 is plenty good enough for me. Anybody that's dealing with AC parallel circuits, if you ever did want to know what the total resistance of the parallel circuit was, taking it to the 10th power or even maybe the 100th power, in this case it comes out at 4.8. Close enough. Now, as you can see at the bottom of the slide here, I said there is an easier way. There is an easier way. So let's take a look at the easier way. Unless you really get into doing reciprocals or finding the reciprocal of the sum of the reciprocals like we just went through, you can do that all day long. That's more power to you, Daddy-O. But there is a different way, and the other way is to continue to use Ohm's law, like I have here in this slide, and calculate the amperage of each series circuit. All right, so for us to find the amperage, we don't know the amperage in this case, or we started out not knowing the amperage, but we know the resistance of each little circuit, each series circuit. So using Ohm's law, we're going to take the resistance here and divide it into voltage. We know 120 volts is our voltage. We know the first resistance is 40. So 40 divided into 120 is 3. So I have 3 amps in the circuit. And you can see how I've got this filled in on down the parallel circuit. We've got 30 divided into 120 is going to give us 4 amps. We've got 20 divided into 120. That's going to give us 6 amps. And then we, last and famous, we got 10 ohms resisted divided into 120, and that's going to give us 12 amps. So what do you do with that? You find the total amperage of the circuit. In this case, it would be 25 amps. Then continue to use Ohm's law to find the total resistance. Okay, so 25 amps divided into 120 volts, as it shows down here, 4.8 ohms. Close enough. And that's my little thing on Ohm's law. I hope this is helpful for you. As you know, or as you probably have found, we have worksheets that we use in the course. This is out of course 111. Here's the simple series circuit worksheets for a simple series circuit. You have the voltage. We want you to find the amperage, the resistance. We give you 2 values for each circuit, and your job is to find the other 2 values. And your instructors, your faculty, love seeing these come in with the right answers on them. And we also have this one, this worksheet for parallel circuits. Same thing. Going to give you the ohms resistance. We want you to know the amperage, and then give us resistance total. So that's pretty much it on this little tutorial. I hope it's helpful for you, and just have a great day. Thanks.